2025 aspirants. So I welcome you all to this master stroke series, and today we are going to complete the chapter equilibrium. Okay, both chemical and ionic equilibrium I'll be covering, so you don't have to worry. I'll be discussing all the concepts in detail. And remember one thing, this is a PU1 chapter, so the weightage of this chapter is very less, so you don't have to go very much in detail. You can just focus on the important formulas that I'm telling you. Do some question practice which I'll be giving you. Obviously you can do practice questions from this particular formulas, then you are set for this chapter. Okay, so now going to the first thing that you should be knowing is, so I'll just tell you in detail. I have given you what all things we are going to study, but let me give you in this form. Okay, so what is the weightage of this chapter? Why should we be preparing for this chapter? So definitely you can expect 1 to 2 questions from this particular chapter. Okay, that is from where you will definitely get questions. Very easy formula based questions are coming, so no need to worry. You can just focus on the formulas and get master this chapter. Okay, so in this video what all things we will be studying. So we will be studying what is equilibrium, types of equilibrium, expression for Kc. Then we have applications of Kc, stoichiometric coefficient and Kc, factors affecting equilibrium, acids, bases and salts, salt hydrolysis, buffer solution and solubility product. Okay, so these are the important topics that we have to cover today. Okay, quickly we will cover, because I told you it is a PU1 topic, not much of the content you need. I know this is a very difficult chapter, but yes, for KCET, if we just study this chapter smartly, then we can target this particular chapter. Okay, so next if I just one second, I'll take the clicker here. So next, if I see what is exactly equilibrium. So equilibrium means two opposite forces, or you can say two opposite process, okay, occurring together at the same rate. Okay, like for example, if you consider evaporation and condensation, you consider melting and freezing. So when two opposite process occurs at the same rate, we call it equilibrium. Second thing, for equilibrium the condition is you should have the concentration will remain constant. Okay, when the equilibrium process is there, like let me give a very simple example. Imagine you have a container here. Okay, you have 1, 2, 3, 4 and 5. There are 5 particles in the liquid phase. Okay, there are 5 particles in the liquid phase and there are 3 particles in the gaseous phase. Okay, now suppose that there is an equilibrium attained here. Okay, the system has attained equilibrium. If the system has attained equilibrium, then what will happen? One particle will go to the, so there are 2 processes happening here, that is evaporation, okay, and condensation. Okay, evaporation and condensation. So in evaporation what happens? One of the particle moves to the vapor phase. Okay, one of the particle moves to the vapor phase while the other particle comes to the liquid phase. Now suppose one particle has gone to the vapor phase. Here I will get this particle, I'm marking it with star for example. Okay, now this one I'm marking with a tick. Okay, just to understand. So what will happen? See, this particle has gone to the vapor phase, so I can erase this one. Now this particle is coming to the liquid phase, so it will be so this one will be here with this one. So now you see both the processes happening, that is evaporation and condensation is taking place, but the rate of evaporation, that is one particle is going and one particle is coming, that is equal. So that is why the concentration remains same. Now you can see 3 particles are there in the vapor phase and 5 particles are there in the liquid phase. Okay, next, the thing that we should be knowing is that this system or any equilibrium can only be possible in a closed container. Okay, it is not possible in an open container, it is possible only in a closed container. Okay, next, types of equilibrium. So basically we have 2 types of equilibrium, physical equilibrium and chemical equilibrium. Physical equilibrium means what? Physical equilibrium means suppose a reaction is there. Okay, how is equilibrium denoted? For example, I am writing A plus B gives you C. This is my one reaction and this symbol represents that the reaction is at equilibrium. Okay, now physical equilibrium means where the physical processes are considered, not chemical reactions. For example, freezing and like I told you, liquid evaporation and condensation, these are physical processes. Melting and freezing, these are physical processes, right? So these type of reactions where there is physical processes involved, that is called as physical equilibrium, and those processes where exactly the chemical reaction takes place, that is your chemical equilibrium. Okay, next we have one more type of equilibrium, that is your homogeneous equilibrium. Homogeneous equilibrium means in a reaction, if the particles, or you can see the reactants and products, are in the same phase. So you can see here gas, and here gas. Okay, here also it is aqueous and this is also aqueous. So when the reactants and products are in the same phase, then we call it a aqueous phase, or you can say that the reaction is, you are having homogeneous equilibrium. Next we have this I will explain after some time. Okay, I have given some formula here. I will be discussing this one next. Okay, I'll come to those topics, do not worry. Now what is heterogeneous equilibrium? You can see that the reactants and products are in different phases. Here the reactant is in solid phase, products are in the solid and gaseous phase. Okay, next, coming to expression of Kc, this is very important. How do we write the formula of Kc? So if you have a reaction where x into a plus y into b gives you L into c plus m into d, then the equilibrium constant, that is Kc, is given by the product concentration raised to power of their stoichiometric coefficients divided by the reactant concentration raised to the power of their stoichiometric coefficient. C gives you L, D gives c to the power of L, d to the power of m, a to the power of x, and b to the power of y. That is called as Kc, or equilibrium constant. Next, Kp. Kp is what? Kp is what? Pressure. The same thing you have to write, but in terms of pressure, not in terms of concentration. So pressure of C to the power of L, pressure of D to the power of m, pressure of A to the power of x, and pressure of B to the power of y. Okay, next we have here, we will understand about, okay, here I want to just give you one thing, that's the relation between Kp and Kc. So Kp is equal to Kc into RT, okay, to the power of delta Ng, where Kp is the equilibrium constant at pressure, Kc is the equilibrium constant for concentration, R is the gas constant, T is the temperature, and delta Ng. Delta Ng is what? Delta Ng is the number of moles of products minus the number of moles of gaseous reactants. Okay, fine. Next we have applications of Kc. So application of Kc, we have predict the extent. So what are different applications of Kc? The first one is to predict the extent of the reaction. The second one is to predict the direction of the reaction. The third one is to calculate the equilibrium concentrations. Okay, so what is this extent of reaction? So if the Kc value is very high, okay, so you can see here expression for equilibrium constant is applicable only when the concentration of the reactants and products have attained a constant value at the equilibrium state. Independent of initial concentrations of the reactants and products, equilibrium constant is temperature dependent and have only one unique value for a particular reaction. So whenever I am writing this equilibrium constant formula, right, this, what does this concentration mean? These are the concentrations when the reactant has already attained the equilibrium, and at that time what is the concentration of C, D, A, B, that is what is your equilibrium constant. Okay, so yes, predict the extent of the reaction. So if the K value is very high, that means the reaction is towards the product. If the K value is very low, that means the reaction is towards the reactant. It is not product favorable. Okay, so we have here next one, sorry. Okay, to predict the direction of reaction, this is very important. So suppose I have a reaction that is A gives B plus C. Okay, just I'm writing like this. Now I can write the value of Q. What is Q here? Q is called as your reaction quiescent. Okay, Q is called as reaction quiescent. Okay, and Q is equal to, suppose I'm writing like X, Y, and Z. Okay, so Q will be equal to C to the power of Z, then you have B to the power of Y, okay, and then you have A to the power of X, right? Now what happens? You have to find this value of Q. Now what is this concentration now? This is, okay, I have done a small thing here. You don't have to put this one. Okay, so now see, so here it is the concentration of A, B and C at any time. It is not required or it is not mandatory that the concentration has to be at equilibrium. It is not like that. So you have to find the value of Q. Now you also have to find the value of Kc, that is your equilibrium constant. For this reaction I will write like this: A gives me B plus C, okay, and you have X, Y and Z. So you have here C to the power of Z, B to the power of Y, and then you have A to the power of X. Okay, so now this is when the reaction has already reached equilibrium. This is when the reaction is not at equilibrium. So now you have to compare. So you have to compare the value of Q and Kc. If Q is greater than Kc, okay, if Q is less than Kc, and if you have Q equal to Kc. Now if Q is greater than Kc, then the reaction has to shift in backward direction. Okay, if Q is less than Kc, then reaction has to shift in forward direction. Okay, if Q is equal to Kc, then the reaction is at equilibrium. Okay, clear? Next, what is the relation between delta G and K? So we can also calculate delta G using the value of K, and that is delta G is equal to minus 2.303 RT log of K. Okay, so this is the formula, and here R is your gas constant, T is temperature and K is the equilibrium constant. One second. So here R is your gas constant, T is your temperature and K is your equilibrium constant. Okay, so next what we have here is, just a minute, okay, so now what is the relation between the stoichiometric coefficient and Kc? Okay, this is something very important that you should be knowing, and from here questions have been asked repeatedly. Okay, so let us focus on this one. So now suppose you have a reaction like this. A gives you B plus C, okay, and this reaction equilibrium constant is suppose K1. Okay, for example, this reaction equilibrium constant is K1. Now what I have done, I have reversed the reaction. So that is like B plus C is giving me A. Okay, so what is K dash here? K dash is 1 by K1. So when you reverse the reaction, the equilibrium constant becomes inverse. Okay, next you have this reaction. A gives you B plus C. Okay, now suppose this whole reaction is multiplied with N. So I will get NA is equal to NB plus NC. Okay, now suppose, as I said, this reaction equilibrium constant is K1. Next, K dash is equal to, you have K1 to the power of N. Okay, next we have if the reactions are added. So if you have two reactions like A gives you B plus C, and suppose B plus C, as one more reaction is giving you D plus E. Okay, so this reaction is having K1 and this reaction is K2. Now if I add both of this reaction, what I will get? A gives you D plus E. Okay, now when I'm adding these two reactions, the new reaction here, the K dash, it will be equal to K1 into K2. Okay, so please remember this formula is important. When two reactions are added, their equilibrium constants are multiplied. If the reactions is reversed, the K becomes inverse, and if you multiplied one number to the whole reaction, then it will become K1 to the power of N. Okay. Next we have the factors affecting the equilibrium. Here the first factor is Lee-Chatelier principle. Now according to this Lee-Chatelier principle, what happens is, if a system is already at equilibrium and you are trying to disturb the equilibrium, so how will you disturb the equilibrium? For example, you can either, there are four factors by which you can disturb the equilibrium. You can change the temperature, concentration, pressure and volume. Okay, so if you are changing the temperature, concentration, pressure or volume, then the equilibrium will be disturbed. Now once the equilibrium is disturbed, once the equilibrium is disturbed, the reaction will try to follow, or the reaction will try to move in such a direction that this disturbance that you have caused can be nullified or can be nullified. Now I'll give you a simple example. This Lee-Chatterley principle statement is very, very complicated, but I'll give you a very, very simple example to understand it. So let us consider a reaction. A gives just a minute. Okay, I'll go, so we have four factors like temperature, concentration, pressure and volume. Okay, so just a minute. So I will focus on concentration here. See, suppose you have taken A gives you B plus C, a reaction is there. Okay, now suppose in case you have increased the concentration of A, you have increased the concentration of A, what will the reaction try to do? Reaction will try to decrease the concentration of A. You have increased the concentration of A, reaction will try to decrease the concentration of A. And see, now when you want to decrease the concentration of A, that means whatever A you have added, that should be consumed, and to consume it should go in forward direction, right? It will not go in backward direction. In backward direction, what happens? More if you add A, and if the backward reaction also A is happening, then more A will form. So basically what you have to remember, or what you have to understand is, if I am increasing the concentration of A, reactant will try to decrease, or the reaction will try to decrease the concentration of A. If the reaction is try to decrease the concentration of A, that means reaction has to go in forward direction. Now if you have here A like this, concentration of A is decreased, or let me take concentration of B is decreased, you are removing the B, that what will reaction try to do? Reaction will try to increase the concentration of B, and to increase the concentration of B, more B should be formed, and that is why it will be in forward direction. Now let me take one example. You are increasing the concentration of C. You are increasing the concentration of C. The reaction will try to decrease the concentration of C. To decrease the concentration of C, what will happen? You have to consume this C, and to consume this C, it has to go in backward direction. So this is the order. So basically what conclusion I can take from here is, just a minute. What conclusion I can take here is, if you increase the concentration of reactants, then reaction will go in forward direction. If you increase the concentration of products, okay, then reaction will go in backward direction. Similarly, if you decrease the concentration of reaction, forward reaction. If you decrease the concentration of products, it will be in forward direction. Okay, I hope this is clear. Okay, next, temperature, you should be very clear. If it is endothermic reaction, if you increase the temperature, forward direction. If you decrease the temperature, backward direction. For exothermic, if you decrease the temperature, forward direction. If you increase the temperature, backward direction. Okay, next we have pressure. So now see, pressure is something, suppose I write a reaction like this, N2 plus 3H2 gives 2NH3. Okay, so now for example, what happens? You have increased the pressure. Okay, you have increased the pressure. What will reaction try to do? Reaction will try to decrease the pressure, right? If you increase the pressure, reaction will try to decrease the pressure. Now decreasing, we know that pressure is directly proportional to number of moles. So if I am decreasing the pressure, the reaction will go towards less number of moles. And if I see this side there are 4 number of moles, this side it is 2 number of moles. So reaction will go towards less number of moles. So I will put this side. So I can say that reaction will go in forward direction in this particular example. It is not always like this. Okay. So basically what I can conclude here is, if I increase the pressure, reaction will try to decrease the pressure and move towards less number of moles. Okay, now if pressure you are decreasing, reaction will try to increase the pressure and it will go towards more number of moles. Clear? Okay. Next we have volume. So volume and pressure are very much related. So now see, if we can consider, you should remember that pressure is inversely proportional to volume. Means if I say that if I want to increase the pressure, that means I should have decreased the volume. Okay, so let me take you an example of this same thing, that is N2 plus 3H2 gives me 2NH3. Okay, suppose this reaction is there. Now what is happening? Suppose let us consider that the volume is decreased. Okay, or I'll say that, just a minute, let me consider here like the volume is increased. Okay, so if the volume is increased, that means what? If the volume is increased, that means I want to decrease the volume. This is what the action has been taken. The response is to decrease the volume. And if I want to decrease the volume, what should happen to the pressure? The pressure should increase, right? And if the pressure has to be increased, then it should go towards more number of moles. Okay, so if you are increasing the volume, reaction will try to decrease the volume, and to decrease, so see, when you are increasing the volume, reaction tries to decrease the volume. Decreasing the volume means towards, I can say that increasing the pressure. These two are equal, okay, because they are inversely proportional. And to increase the pressure, we should go towards more number of moles. So you can see this side it is 4, this side it is 2. More number of moles means it is this side. So I can say that backward direction, the more it will go. Okay, so there is no role like that. So I can say that if you are increasing the volume, reaction will try to decrease the volume, or I can say that it is equal to increase of pressure and reaction will go towards more number of moles. Okay, similarly, if you have decreased the volume, reaction will try to increase the volume, that is equal to decreasing of pressure, and that means it will go towards less number of moles. Okay, clear? Next, yes, here there is something that is addition of inert gas. If you are adding any inert gas, addition of inert gas. Okay, so now if you are adding anything at constant volume, then there is no effect. Okay, if you are adding anything at constant volume, there is no change in the pressure or no change in the equilibrium. If you are adding at constant pressure, okay, if you are adding something at constant pressure, and to maintain constant pressure, what you have to do? You have to increase the volume. Okay, so what happens if a system is there at constant pressure, okay, and you have added something to that? To maintain that constant pressure, what will happen? The volume will automatically increase. The system will adjust itself so that the volume has automatically increased. Now if the volume has increased, what does the reaction try to do? Reaction will try to decrease the volume. Decrease the volume is equal to increase the pressure, right? And if it is increasing the pressure, it will go towards more number of moles. More number of moles. Clear? Okay. Next we have here catalyst, and in the catalyst also there is no effect. Okay. For catalyst also there is no effect. Fine. Next we will discuss about acids, bases and salts briefly. So I have to explain acids, bases and salts. We have three different theories. One is your Arrhenius theory, another is your Bronsted theory, another is your Lewis theory. So according to Arrhenius theory, acid is something which can donate H+. Okay, so this is the definition of acid. And what is a base? Base is something which can donate a OH minus. Okay, so this is your Arrhenius concept. Now next we have here Bronsted concept. According to Bronsted concept, acid is something, this is the same thing, that is donates H+. Okay, and base is something which can accept H+. Okay, now let me take you an example for this one. HCl plus water. Okay, so what will happen? This one will, as an acid, it will donate H+. So here what it has donated H+, so this is an acid and you will get Cl minus. Now what will happen? This H2O will accept the H+ that is released here and it will form H3O plus. Okay, Cl minus plus H3O plus. So now what happens here? See, this is your acid. The species that is formed after losing H+, this one is called as your conjugate base. Okay, now suppose this is behaving as a base. Okay, this is behaving as a base. Now if this is behaving as a base, the species that is formed after accepting H plus, this is your conjugate acid. Okay, so acid is something which can donate H plus, and after the species that is formed after the donation of H plus is called as conjugate base, and base is something which can accept H plus, and the species that is formed after accepting the H plus is called as your conjugate acid. Okay. Next we have Lewis theory. So according to Lewis theory, what I can say, acid is something which can just a minute. So please note down these things. Just a minute. Yes. So acid is something. Just a minute. Yes. Acid is something which can accept lone pair, and base is something which will donate lone pair. Okay. Clear? Fine. So here I'll give you an example as well. So suppose for example you have AlCl3. This is an example of Lewis acid. Okay, it can accept lone pair of electrons. If you consider NH3, okay, this is having lone pair, and this can donate electrons, and it will behave as a Lewis base. Okay. Next we'll come to the ionization of acids and bases. So see, acids and bases can be classified as strong acid, weak acid based on their dissociation. Okay, so strong acids and bases are those which can dissociate completely. Means if you take them in water, you will get all the ions in the form of ions. For example, you can take HBr, you will get H plus and Br minus, HCl, H plus and Cl minus, HNO3, H plus and NO3 minus, H2SO4, H plus and SO4 2 minus. So these are your bases, strong bases and strong acid. Similarly, weak acids and weak bases will dissociate partially. Means if I take HF, okay, and I leave it in water, then I will get three types of species. I'll get H plus, I'll get F minus, and I'll get HF also. Means there will be some HF which is not dissociated. Okay, it is not completely dissociated, like that also particles will be there. But if you take here HCl, there will be no HCl as it is. It will always be in the form of H plus and Cl minus. So that is the meaning of complete dissociation and partial dissociation. Next, here this is one important point. So if an acid is very strong, means it is undergoing complete dissociation of very strong acid, the conjugate base that is formed here will be the weakest one. So if HCl is suppose I compare HCl and HF, okay, both are acid. HCl is a stronger acid, so its conjugate base will be Cl minus and its conjugate base will be F minus, right? 1 second. Yes. Okay, so yes, so its conjugate acid is Cl minus, and this conjugate base is Cl minus, and this conjugate base is F minus. Now if I compare Cl minus and F minus, then because it is a stronger acid, its conjugate base will be weak. Okay, so Cl minus is a weaker one, F minus is a stronger one. Okay. Next we have here something that is related to the acids and bases. So you should be knowing that H plus and OH minus, this is called as your ionic product of water, and this value is 10 to the power of minus 14. Okay, Kw is equal to 10 to the power of minus 14. So here pH is equal to, is written in the form of minus log H plus POH. Okay, 1 second. Just a minute. Yes, so POH is equal to minus log of OH minus concentration. So pKw, so if I take here, I will get pH plus POH is equal to 14. pH plus POH is equal to 14. Okay. Next here we have something related to the acid dissociation constant. So Ka is your what? Acid dissociation constant. Ka is equal to C alpha square by 1 minus alpha. Now what is this alpha value? Alpha is your degree of dissociation. Now see, as I told you, the acids, weak acids will not undergo complete dissociation, right? So there will be 20% dissociation, 40% dissociation, 50% dissociation, 100% dissociation. So if there is if it is a weak acid, then definitely there will be 1 degree of, yes. So if there is a weak acid, then definitely we will have this alpha group, okay? So if we have a weak acid, then definitely this alpha will be there. So now for example, suppose the initial concentration was C and this was 0 and this was 0. Now after that what happens? Alpha amount, for per mole alpha amount has dissociated. For C moles, how much will dissociate? C alpha. So at equilibrium we have C minus C alpha and C alpha. Now if I want to write the equilibrium constant, we denote it as Ka. Then what it will be? It will be H3O plus concentration, A minus concentration and HA concentration. So here H3O plus will be C alpha, it will be C alpha, and this is C into 1 minus alpha. So when this is cancelled, we get C alpha square by 1 minus alpha. Okay, clear? Fine. Now here this Ka can also be written in the form of pKa, that is pK is equal to minus log of Ka. So here you remember, if Ka value is very high, okay, that means acid is strong. Okay, if Ka value is very high, then it is a strong acid, and at the same time if Ka value is very high, that means pKa value is low. That also means a strong acid. Okay, so please note down this one. Okay, next we have the same thing for base as well. The same way we can discuss. And what's the relation between Kb and Ka? Ka into Kb is equal to Kw. Here also, if we have a strong base, okay, if we have a strong base, then it will have high Kb value, okay, and low pKb value. Clear? Okay, so Kb into Ka is equal to Kw. And if you just take logarithm, pKa plus pKw is equal to pKw. Okay, fine. Next we will discuss here so ionization constant. So those acids, okay, which can give you more than one acids, means more than one H plus. So you can, for example, H2X, it will dissociate to give you H plus and HX minus, then HX minus will dissociate to give you H plus and X2 minus. So suppose this dissociation constant is Ka1 and this dissociation constant is Ka2. So what will be the order of Ka1 and Ka2? So you should be knowing that Ka1 will always be greater than Ka2. So now why? Because see, here what happens, you are removing one H plus from a neutral atom, but here you have to remove the H plus from a negative ion, right? So this negative ion will hold the H plus very tightly. So it is not easy to remove this H plus easily. So that is how we will get H plus and HX minus, H plus and X2 minus. Okay, fine. Next we will go to ionization of acids and bases. So here we have, one second, yes. So strength of an acid, on what factors it depends? It depends on the HA bond. So you know HI bond is very weak because of the size, so it can easily donate H plus. So this is the order that is followed here. Next, if you compare polarity of CH bond, so more is the polarity. When you are comparing the acids along a group, you should focus on the HI bond, HA or HX bond strength. When you are comparing along the period, there is no much difference in the size. You should be comparing about their electronegativity. So here carbon hydrogen H plus removal is difficult as compared to HF. Next we have something called as common ion effect. So common ion effect you can easily understand if you have studied Le Chatelier principle. Okay, so it can be defined as a shift in the equilibrium adding a substance that provides more of the ionic species already present in the dissociation equilibrium. It reduces the dissociation. Let me take an example. Suppose I have HCl in water. It is dissociating to give me H plus and Cl minus. Okay, now this is there in this container. Okay, in the same container, suppose I add NaCl, then what will happen? It will dissociate to give me Na plus and Cl minus. So for this particular reaction, what is the environment? in the environment we have excess of Cl minus, right? So Cl minus is the common ion. The number of Cl minus has increased, and that is why what happens, we have studied that if you increase the product concentration, reaction will go in backward direction. So whatever Cl minus if you add, it will go in the backward direction and HCl concentration will increase. Okay, so that is your common ion effect. Now coming to salt hydrolysis, so we have basically, yes, okay, so now see, salt hydrolysis means when you take a salt, okay, and you put it in the water. How does it react with the water? That is called as salt hydrolysis. So we have 4 types of salt, right? We have salt of strong acid and strong base. We have the salt of weak acid and strong base. We have the salt of strong acid and weak base. We have the salt of weak acid plus weak base. Okay, now out of this one does not undergo salt hydrolysis, all of these 3 will undergo. So we have weak acid plus strong base. In that case, what is the pH of the solution? pH will be 7 plus half pKa plus half log C. Now if you have a salt of strong acid and weak base, right, then it will be 7 minus half pKb minus half log C. And then if you have a salt of weak acid and weak base, it will be 7 plus half pKa minus half pKb. So you have to understand these formulas. Okay, so I just want to explain here something what exactly happens. So let me take an example of weak acid. For example, CH3COOH, okay, and I take a strong base, NaOH we can take, right? Now when this one will react, what I will get? CH3COONA, right? And water I will get, CH3COONA plus water. Now see, this one has 2 ions, that is CH3COO minus Na plus, and I will get water, and water will have H plus and OH minus. Now what will happen? Understand carefully, this ion and this one will react. So basically what I'm saying, this type of salt which is made up of a strong weak acid and a strong base will undergo salt hydrolysis, or it will break and will react with water. Okay, next we have already seen this formula, so please note down these formulas. Then coming to buffer solution. So what is a buffer solution? So buffer solution is a special type of solution where if you add any acid or a base, the I can say that the pH of the solution does not change. Okay, the pH of the solution does not change. Now why does this happen, or what is the role for that? That is because the buffer solution is made such that so that it can resist the change in the pH. So we have here 2 types of buffer. One is your acidic buffer and the other one is your basic buffer. Okay, so I will explain what is this. Okay, yes, so acidic buffer is made up of what? You have a salt of weak acid and strong base plus weak acid. So if you have acidic buffer, you should take a weak acid, okay, and the salt of weak acid plus strong base. Okay, so you should have a weak acid and the salt of weak acid and strong base. So for example, if you have CH3COOH as the weak acid, and you should be taking the salt of weak acid and strong base, so that is CH3COOH, and its salt with a strong base NaOH, so you will get CH3COONA. Okay, so next, if it is an acidic buffer, the pH value will be less than 7. Okay, now coming to the basic buffer. So basic buffer is made up of weak base, okay, and the salt of weak base plus strong acid. Okay, weak base plus the salt of weak base and strong acid. So if you have NH4OH, okay, so for example, if you have taken NH4OH and you have taken NH4Cl, okay, NH4OH and NH4Cl. So NH4Cl is made up of a weak base and a strong acid, and since it is a basic buffer, the pH will be greater than 7. Okay, next we have here solubility. So how do we explain solubility? Solubility depends on 2 factors, that is your lattice energy and the solvation enthalpy. Okay, so as a general rule, for a salt to be soluble or to be able to dissolve in a particular solvent, its solvation enthalpy must be greater than the lattice enthalpy. So lattice enthalpy is the energy required to break the molecules into the ions. For that we need energy, and solvation is when these ions are hydrated, energy is released. So more energy should be released than the amount of energy required to break the bond. Okay, so that is why it is solvation enthalpy should be greater than the lattice enthalpy. Next, coming to the last topic, solubility product. So suppose you have a salt like AXBY. Okay, how will it dissociate? It will give you X times A plus and Y times B minus. Okay. Okay, so for any salt of AXBY, the solubility product is denoted as KSP, and it is denoted as X to the power of X, Y to the power of Y, in S to the power of X plus Y. I'll give an example. For example, you have MgCl2. Okay, suppose the solubility of this one will be Mg, that is 1, X is 1, Y is 2. So 1 to the power of 1, 2 to the power of 2, S to the power of 3. So you have 4S cube. Okay, next you have aluminium chloride. Okay, so here we have 1 and here we have 3. Okay, so this is 1 and this is 3, X to the power of X, Y to the power of Y, and you have S to the power of X plus Y. So that is 4. So you have 3 3s are 9, 3s are 27 S. Okay, so students, this is all about equilibrium. So I told you, you don't have to go to be very deep into the equilibrium if you just remember these formulas, and I'll be giving you question practice. If you do those question practice, then you will be able to tackle all the questions from this particular chapter. Okay, so please do not worry. I know many of you must be scared of this chapter, but this is what only you have to do. Okay, so all the very best, and please keep learning, and let's see in the next class. Thank you for watching, and do not forget to subscribe the channel.